Tuesdays, I actually do like Monday plus half of Wednesday, and then Thursdays is like the less half of Wednesday, and Fridays here. It's just like, if I try to stay on pace with it, I do 1.5 lectures a week. So the first, I gave them feedback on the questions you asked. I'm going to give you feedback on the questions they asked. One of the questions was, what is the point at which logistic regression or multi-logistic regression starts to suffer some diminishing returns? And the answer to that is usually around a predictor factor of about 3 to 5. All right, 4 or 5 is usually the upper band. Reason why I say that is we need to understand when to use these tools, and I would say that overall, some of the capacities of the linear discriminant analysis give us an advantage over the standardized logistic regression by allowing us to pick the axis of projection that has the direction of least overlap, right? So maximum separability. So we're going to look at the idea of maximum separability. If you simply approach each individual class likelihood as a singular value, you end up with something that is a bit like our standard notion for the Bayesian theorem, right? But the Bayes' theorem has limitations. We'll talk about another methodology briefly, which is called the naive Bayes analysis. And naive Bayes does the same thing or a similar thing to the max log likelihood classifier. Right, the max log likelihood, if you remember back here, go back a little ways, look at it real quick. Max log likelihood classifier is an optimization that runs in the opposite direction of something like MSE, okay? Mean squared error would be an implication of attempting to minimize the difference between the target class and the output prediction, right? The inference. The inference is what we get from our hat function, and in this case, our hat function is actually the L, the linear discriminant. The linear discriminant provides us with an assessment of the likelihood for the in-class elements and outside class elements. So this is, in fact, for each one of these, if you think about it, optimization is attempting to maximize the within-class likelihood characteristic. So what is the desirable likelihood characteristic? The desirable likelihood is 100% confidence, right? So if I say my placement of the discriminant is put in place such that I maximize that if it's a 1, then I will have my likelihood estimate as close to 1 as possible. So it is the delta between 1 and whatever the probability estimate is. That is how this calculates, right? Which is a type of Bayesian inference for one versus the rest classifier. And this system for multi-logistic regression has a very similar functionality to it in the effect that we have, as we look over here at C, this is just a multilinear system. What do multilinear systems look like? They're high dimensionality surfaces, essentially, right? So once you get past the single dimension line, you get into planes, you get into hyperplanes. So now we have a singular linear operation being applied to the nonlinearity of the natural exponential. And then we're taking the ratio of this one here. It says the probability of being a member of class K, right? K elements within the desired class set C, right? So there is a set C with K members. So if you are K1, right, you're the first K, then we're going to say that this equation or this discriminant matches your inclusion. This is essentially the above the line characteristic. We see a summation down here for K elements, right? This is the matrix K, which is going to contain all of the classes. So we will have multiple linearities that describe all the classes. So in this case, this says it is the target discriminated from everything that is not target. Essentially, that's what we're looking at with regard to these systems. Now, I'm going to draw something because I think it's useful. Let's first look at a relationship between three classes that were given previously, right? We have a few X's, we have a few O's, and then we have, let's say, hashtags over here, right? If I start off on drawing lines, let's just start off with a strictly linear idea. We know that the linear and the logistic regression tend to follow the same relative pattern. So let's think about this as a multilinear system. So let's say I draw a line by projection that separates X from the remainder of the samples. And then I draw a line that separates O from the remainder of samples. Do I need another line?
Yes.
No, I don't. The reason being is if I say it isn't an X and it isn't an O, then it's a hashtag. So truthfully, we actually do not need K lines to create a K class system. We need K minus 1 lines to create a K class system. Now partially this is confusing because when you first look at it, you go, well, if you consider the spatial distribution here, then things that are in hashtag are obviously much more likely to be selected because they have a much larger area, right? But relative to each grouping, this is the O line, right? You don't consider the X line. So cover that up and consider that is all area that is O. Cover this up and say that is all area that is X. So the relative area, or the divided area, is just each line looking at it from each direction. It's the composite of all of these that essentially informs us that if you are in this side of the system, that you are in fact a hashtag, right? So it's the total probability theorem, the notion of it must be one of the three that gives us the inference consideration of class membership likelihood. Now we're going to do this for higher dimensionality systems. It's going to start getting really hard to do past a certain number of degrees in terms of how many K classes we have. So too many classes is going to create problems with the linear and logistic regressions. They're going to make it incredibly hard for us to do it with respect to just the data points. Right? What's one of the biggest problems with working with just the data is that if I do something like a K nearest neighbor approximation, then I have to go out and I have to collect and analyze all of the local adjacencies for K of those nearest neighbors, and I have to do that every time I get a new sample. But I don't want to do that because I recognize that that is a little bit frustrating and costly for me. Everybody tracking with what we're doing up here? I think we covered this already a little bit at the end, so I'm not going into it in high detail. But I think everybody can see this. This is a natural consequence of what we've been doing so far, just extending it out to multilinear class. This is, as I said beforehand, once we've kind of spent time doing these things in the past, it's just like, okay, here's a way we do this with this stuff. And you start to be able to read these equations pretty quick because you start to see patterns inside of them. Recognize here, if we look at this as probability, if I take the probability considerations of the true target, right, the membership for a class given all class elements, now I'm using this as a data-driven approach. So it's going to be the error metric is going to be minimizing the delta between the probability of the true class label for K and whatever this model comes up with probability, right? Most probability models are not going to come back with ones. They're going to come back with like 0.78 or something like that. But the target label is a 1. So we say the target label was a 1, but we guessed that it was 78% a 1. We would say that's pretty good, right? We adjust some parameters of the model and then we move a line over and we say, okay, that one's a 76% a 1. Say, no, that's less than I want it to be. I'm less confident in it. That's a poor model. Move the line over the opposite direction and say, oh, now it's an 81% a 1, a 0.81. So you say, yeah, that's better. That's closer to the target. So the idea of the optimization at that point in time simply becomes narrowing the distance between the goal and the target, which is very similar to the methodology which we did the calculation for error with respect to linear regression. So when we think about the way in which we calculate error and an iterative way in which we can move the line around and adjust it parameter-wise in order to try to get the maximum likelihood assessment for all classes in the system, this just becomes an exhaustive process of attempting to try to find the perfect balance between all of the coefficient elements and the desired target inputs, right? Computationally intensive is the key factor here. It's relatively high end as far as I have to calculate. Every time I adjust a factor, I have to calculate for all values. So that one is a little costly. It starts to add up, especially when k gets high, and especially whenever your sample number is high. Doing these regressions gets functionally costly. So we also call these multi-class logistic regression, is also known as multinomial regression, right? Rather than polynomial, we say poly is kind of like the characterization for a multi-linear system. We say that multi-logistic regression is multinomial as a result of it being a ratio of exponentials. All right, so let's talk about the next item here. Next item up for bid. So this is going to be a potential solution to the problem we just ran into, which is whenever n gets high and whenever p gets high, we have high dimensionality relative to the number of features and a high number of samples, then the relationship becomes difficult to sort out. We won't really be able to see clearly exactly the reason why I say it's difficult to sort at the moment, but if you guys do comparison to between methodologies at different levels of the complexity system, like as p increases or as the features you're keeping increase, you'll note that the linear discriminant analysis or discriminant analysis will start to perform or be more stable in terms of performance further out in terms of the number of p, that is the number of feature elements within the system, and k, number of class elements. All right, so we have three items we're working with here. We have n, that is the number of samples in the system. Really the only reason why it makes a difference with regard to n is processing complexity. If I have a really high number of samples, I have to go through thousands of calculations in order to be able to update anything. So the more elements n I have, the more complex it becomes to compute any new adjustment. Discriminant analysis actually allows us to overcome that problem by working as what is called a generative methodology. So we see here the necessity or the implication of Gaussian distribution as a way of describing or a way of working with the values that we're going to be encountering. We say that the data set's components, each class has its relative underlying distributional characteristics. So if I see a certain number of values, I'm going to recognize that there's probably some underlying system to this, and I'm going to make an inference, okay? I say this is what my data set looks like, this is my projections of my values and my distribution of values within the system. I'm going to make an inference, and the inference is that this is likely governed by some type of normal distribution. Why do I say that that's a safe approximation? Because almost everything in the natural physical universe operates according to that normal distribution. Everything from planetary orbits to ballistic trajectories, all this stuff has these normal curvature processes. Also distributions of population dynamics, from traits to performance metrics, right? So if you go to class, and we tend to notice that there is a curvature within the class grouping that has a centralized distribution, right? We'd attempt to fit that to a somewhat normal distribution, that bell curve. So each of these points here are an indication of the generalized shape of that curvature. So what we're actually going to do is we're going to create a normal distribution with properties that match the data set that we've been provided with, okay? We're actually going to generate a probability distribution function, probability density function here, related to the data set we have. Now, if I have this function, and I have the general shape of it, knowing that it is a normal distribution, for those of you who've dealt with this beforehand, do I need the data points anymore? Once I project it into the normal distribution, do I need to keep data points? No, I don't actually need data points anymore. These data points are essentially, like I like to say it this way. They are what created the distribution. So we are keeping something about them. But we're keeping general trends within that system, not specific values. So the cool part about this is once we eliminate the necessity of having to deal with this system on a point-to-point basis, our calculations for error are going to be a little bit different with regard to this system. Now, I'm going to show you a graphic here, show you a couple graphics from my supplemental slides. But we're going to first look at the idea of Bayes' theorem again, all right? Everybody should be fairly familiar with this. The probability of membership for K of some specific value X within the array X of all sample data points is equal to the probability of X, right? The relative prevalency of X for a given class times the prevalence of the class over the likelihood of class. This is a density characteristic. So this is a situation where we're determining a posteriori from a priori and likelihood estimates. So we say prior information provides us with the ability to predict future outcomes based upon estimations or assumptions of density. This allows us to import some knowledge from the data set that allows us to be able to create this probability function. So Bayes' theorem in extension places us into a space where we can generalize it to a understanding of the relationship between pi k, right? That is prior. I like to say here, this is an easy way to remember this. I've had students in the past. Pi, right? Pi is prior. Pi is prior. That means what came before. So we often say in the Latin, we say a priori, that which was before. So pi is the prior. Prior says previous indications provide for me the labels of values for member class K. Okay? The density characteristic, f of x, right? We say this is kind of the marginal density characteristic or an indication of membership likelihood, is density for x values in class K or members of class K. So the values of x that are members of class K is expressed as the prior, right, with respect to this. So we say prior times density, prior density, right, relative to prior density for all L of K. What happens here? What does that look like? That's very similar to the multinomial regression we were just working with, right? Singular value relative to likelihood over likelihood of all membership. Honestly, I think in some ways it's like this kind of came before. A lot of it definitely you can see is before is more primitive in terms of calculations, because without the logistics being inputted, this is just pure numerical analysis, the data sets for the points that were provided. Now this is a fairly important formula, and you guys should really be able to look at and see what's going on and be able to describe for me what these pieces are and how relatively they're calculated. From the perspective of knowing what the prior k means, knowing what the prior or the probability with respect to the value of x given the label k, right? Know how to calculate those. Yes?
So what's the down one, the pi L?
Okay, so it's look at what's happening here in front. This is a summation for all L, right, L1 through LK, for pi of L, or f of L, right? So this would be K1, K1, then K2, K2, right? It is the values, it is the samples that were members of that class, right? It is their density times their prior likelihood for each relative class. So expand it out in your mind. It's multiplying summating all of the members of each class, right? It's saying the class target, its relative likelihood of occurrence is what? The simple probability of all classes. So pi of class 1 for the density function of class 1 over pi 1 f1 plus pi 2 f2 plus pi 3 f3 and so on, all the way up to pi of k f of k, right?
Okay.
It's how likely is it relative to how likely all of the others are. Saying prevalence mostly is a consideration here in the sense of the density characteristic, whereas the valuation or total value in the system is accounted for by the marginal a priori likelihood. Two classes, right? A new value. A calculation of new value is going to be based upon relative distance characteristic from the marginal mean of the system relative to the density or spread of the system, right? How it spreads out into the system. So if I have two spreads coming towards each other, how do I determine which class it belongs to? I say, well, it's not only the distance relevant to the class's norm or the class's mean, it's the relative density of the class in the space. That implies the likelihood. So you say you have two groups of individuals kind of grow together, and you just pick an arbitrary location. You're going to look around you, you're going to say, okay, which has the highest population relative to the space? That's the ratio characteristic of density. So we have two densities here. We have a density for the class target, and we have a density for all other class targets. This is the intersection of all these class targets intersecting together. So I can continue out looking at the likelihood of intersections relative to the densities of these populations. Whichever one is both closest and most dense is going to be the most likely, and the one that is furthest and least dense is going to be least likely. Because you're not going to have neighbors around you that are going to justify it. And the relative center is going to be far away. This is like you live in the country and you've got 4 towns around you, right? And you want to know which town you belong in, right? What town am I in, right?
What if you don't want to know?
What if you don't want to know? Then just don't calculate this. Okay? Don't calculate, don't plug in the numbers and you won't find out. Because if you plug in the numbers, you will find out, okay? You'll figure out which town you belong in. However, what happens? What happens if the populations of those cities change? Right? What happens if if people on the outskirts start to, go back into the inner cities or whatever? Then you've got to recalculate the system because the densities have changed. But the densities will change over time. So we calculate densities. We build these densities. These are what I was talking about with respect to density. Okay? This is a 2-dimensional representation of the density graph. But take this in your head, and if you want to turn it into a 3-dimensional one, what do you do with it? Create a surface by revolution. You should be able to do this fairly easily if you've done, even the remotest amount of that kind of calculus, right? To turn this into a bit of a sombrero, this is a smooth hill, right? Centered around the mean of the distribution. So we end up with a circle here that is the base of the distribution, right? These are the circles that I'm talking about here. They start off with a density characteristic, and then we can associate them with relative concentric rings around them, in which the distance of those rings, similar to a topographical map, indicate the relative density of the space. Now, why is it relative density? Because the slope is implying a change in the value over that area, right? A high slope would be a relatively quick instantaneous change. A low slope is a gradual change. So they're spread out over a larger area. So if we're looking here, we're going to look at whichever particular system has the highest relative density characteristic, F, relative to the prior information, right? Prior information is all of the class groupings. So it's saying how many total people live in this space relative to that density. So the one thing that's cool about Bayes and what we call the naive Bayes system is that we're not stuck with having to calculate for just total likelihood of the system. Now we're using likelihood, meaning populational mechanics. So you can have a class that has far fewer members than another one, but has high density. And because it has high density, meaning that they're all really close together, it's highly precise essentially, that if you get close enough to it, the system can acknowledge you as a member of it, simply because of the fact that your likelihood of being a member of another class goes very low relative to that very high density. So you go towards the downtown area, right? You get closer to the downtown area, you see the density of the city increasing. There's more people per unit area, right? Then population density is about per unit area. So the per unit area is a density characteristic, and what is the prior? That is just how many total people there are in the class relative to the summation of all the people in general. So remember we talked about imbalanced classes? What is the imbalanced class characterized? It's where we have one class that's far less populated than the others, right? So that becomes imbalanced, meaning that you don't have equivalent representations. So we said within the basics of logistic regression, you need something close to or near on parity, near on identical between all classes in order to make an equivalent or a fair understanding of the likelihood of membership. That is based upon the prior, okay? The prior says, how many of you are there relative to everyone else? Let's say that we're talking about, minority populations in general. What do we say about minority population? It's less populous. But in certain areas of the city, even though it's a minority, its density can be very high. So if you're close to that region, your likelihood of being a member of that group increases, not simply because of the fact that group is more highly prevalent in the system, but because you're approaching a region of higher density in that area. Everybody getting where I'm coming from? Okay, good. Because this matters a lot. All right, we're not going to use this one. I hate this one. So it's both right and wrong.
And this is chapter 4, your supplemental.
These are my supplemental slides for chapter 4. With the Bayesian theorem probability, we're going to get from this version of the equation, output here, the probability of being a member of class K, right, given some specific value X. This is the plug it into this system in order to get a classification of a new point, right? New point here, we're going to plug that in to the system of all relevant densities. We're going to look at the class target, intended class target, and we'll end up in saying, what is the likelihood of it being class 1 given the specific sample value? Now, what is it based upon? It's saying that given previous values for simple x, right, relative to their density characteristics, we calculated all of these density area estimates. So you're going to end up with k likelihoods. You'll actually end up with a sort of an array here. So if we use what's called naive Bayes system, we're going to have k individual classifiers that are going to give you the likelihood of being a member of that k class. And then we're just going to rank whichever one is the highest. Whichever one you have the highest likelihood of being a member of will be the one that we select. We say, if you're a member of class class 1, or what's likelihood you remember class 1? What's likelihood you remember class 2? Likelihood you remember class 3? If class 3 is higher than either 1 or 2, then we'll say that that is the class, the output class. So how did we do that? We did that based upon a density function estimate. So let's look here at a way in which we can utilize an understanding of the density function estimate for multiple classes in the overlapping space. We talked about the overlap characteristic. The overlap characteristic is in fact bidirectional though, right? The likelihood of being a member of class 1 versus class 2 starts here, right? So this is maximum likelihood. It says as I'm approaching this value, the mean of that distribution, then I'm gradually increasing in likelihood, right? I'm getting more and more likely to be a member of that class. This is sort of coming into the system from the outside. Okay, as I get toward that center, I maximize my likelihood. That is sitting right on top of the mean, right? Where basically everything around me supports my membership of the class. And then past that point, what happens? My confidence drops, right? I say, it's getting less and less certain, right? I'm starting to see people from class 2 popping up along the way. So that as the density of class 1 drops, we have, over here notice, we have an increasing density of class 2. If you think about this, you think about looking down on it from the top, we have a bunch of black dots over here, and then we have red dots over here. The red dots are starting to seed in, right? Start to see those little red circles popping up. Okay, then what happens is the red circles start to outnumber the black dots, right? And then now the black dots are gone, and now everything is red circles again. This system implies what? How do I sort out whether or not a value here is in class 1 or 2? Notice, there's a likelihood of being a member of class 2 in this space. You could be class 2 here. You could also be class 1 here. But relative to the comparison between your likelihood of being class 1 to your comparison of your likelihood of being class 2 is far more likely based upon the prior relative to the density. The previous information relative to these density function estimates. Notice there's no points. I don't use points. I'm not talking about points. I'm talking now about functions that have been generated from those points. I'm talking about that density estimate that I built into a function that I'm visualizing, utilizing that Bayesian theorem. Now what I do here is I make a statement that for the linear discriminant analysis, right, I discriminate between these two groupings based upon the overlapping classes such that given equivalent or identical density characteristics, the value of the discriminant, or the best place to place a separability, is going to be where?
In the middle?
Exactly middle, right? Exactly what? 0.5 and 0.5, right? That is literally going to be the surface of indecision, right? Where it's equally likely that it could be either one. Shift over to even slightly right from that position, and then you're slightly more to class 2. Shift over slightly left. Okay. Hey, you want to have a conversation, go out in the hallway. If you want to look at it from this perspective to say membership in class, probability is going to always be increasing from here for member class 2, always increasing here for member class 1. So everything that's leading toward that center point is going to be decreasing in likelihood for one class, but technically increasing in likelihood for the other, such that the summation relative to the equivalent likelihood becomes identical. So if we go over here and we look at something that's interesting, all right, so this is an alternative perspective. I'm going to pop back to the other slides real quick so I can show you what they say. This says pi, right, prior is 0.5. This is half and half. So what's pi prior? That's relative value or relative representation, equivalent relative representation. Over here I now have a 70-30 split. This means there are more individuals that are members of class 2 than individuals that are members of class 1. It's imbalanced, yes.
So are we safe to say that pi prior on the second graph was the 3?
Was which one?
Is the 30%?
Roughly, yeah.
Okay.
Yeah, you remember whenever we did the one that had the members of the MI, the heart attack case, right? This is roughly what would happen with the heart attack case. We would have the green ones would be the heart attacks, and then the red ones would be the control case. This would be the distribution between density characteristics. There's fewer samples, there's fewer members relative to the total population that are members of the target class. So pi is talking about how many total members there are. Notice the height of the overall distribution is lower because there's just fewer members that make it up, right? It doesn't go as high. So this normalizes the two distributions on the same graphic because the summation of those two densities would be this is a perfectly evenly split system where half of the group is in class and the other half of the group's class. So 200 samples for class 1, 200 samples for class 2. Right, this is the one that's like 160 for one and 302 or whatever it was for the other class. Okay, so rough imbalance as provided. We notice here, I'm going to pop back over to this slide. We say if I have a slight imbalance between the characteristics of the groupings, I could have even the same number of individuals in these groups, because these are roughly the same number of individuals. But because the densities change, what happens? These individuals are over a smaller space, these individuals are over a wider space. So if the individual number is the same, the quantities are the same, pi can be the same, but the distribution characteristic, sigma, can change. The width of that distribution, yes, please.
How important is it to try to be 50-50 versus like 30-70? Or does that even matter at all?
50-50 is always going to outperform any other version of the system.
Okay.
Because it is known and has been seen that most every system will reflect a slight bias towards the more populous class, right? So whichever class is more populated will dominate relative to its region, simply because of the fact that the system says, here's an example I gave in the other class. And it's one of those things where it's like a shock value, okay? The highest cause of death for infants is automobile accidents, right? Do you know that? Why is that the case? Well, because of the fact that they don't really die from much else. So when we think about it in terms of prevalence, we look and say, well, adults, actually automobile accidents are they're not the max fatality, at the highest rate. Matter of fact, they're only in the top 4. Right, but for infants, it's very, very high. The reason why is they don't have causal characteristics for mortality that are related to just old age or like disease-driven death. It's not common, it's not high frequency. So what we might have a tendency to say is it's unsafe for a baby to ride in a car. It's just because of the fact that we don't have information or we don't have quantity for likelihood characteristics in that space. So what we might be saying here is that if we had equivalent number of individuals that were said dying from car accidents versus the infant individuals dying from other maladies and disease-related conditions, that we could say those then become balanced. We balance them with respect to the number of samples in each of those class characteristics. So dying of the car accident, other types of accidental death, disease, poisoning, those kind of things. If we had equivalent grouping members in the class groups, then we would say that we could disentangle them. Their likelihoods would become equivalent to one another. And then the adjacency relative to age could be disentangled at that point in time. We have here a consideration where we say if there are simply more individuals, right? If I have 1,000 individuals in one group and 500 individuals in another group, let's say that the 500 individuals drop to 50% of its density over one standard deviation, right? And the 500 individuals drop to 50% of their density in one standard deviation, and they're overlapped right at that point of half density. We now have 250 in one group and 500 still in the other group. So even though the density here is half, it's still much more numerous, just because of the fact that the initial class was so much more populous. So Bayes' theorem attempts to normalize relative to the populous characteristics. That's what we're trying to do. We're trying to take consideration of likelihood relative to density while removing the consideration, or at least taking into consideration, the total population, scaling it relative to the total population. That's why we do density and prior, both density and prior are utilized. All right, when we talk about linear discriminant analysis, I'm going to throw this in here for a moment. When we talk about linear discriminant analysis, we're actually talking about the utilization of between class spread maximization. Now, I've actually done this previously to describe it in this way, and we'll talk about that in a second. But one of the cool things about the linear discriminant analysis is sometimes we have this nice relationship. Sometimes we have this bad relationship, right? I think I showed you this slide earlier on. This bad relationship says if I look at it from this direction as projected onto x2, right? The relative degree of overlap between those two is so high such that this discriminant is going to be very poor, because it's going to say that everything is going to be about equivalent for quite a while on either side of the system. It's going to be very difficult to differentiate them. This is two things that have relatively poor resolving power. It's difficult to look at them and say, based upon position, based upon prior information, I'm not really sure I can tear them apart. However, if I project it onto a new surface at this angle, right, onto x1, I notice they're very separable, and I only have a very small region of overlap, or a small region of equal likelihood. So how do we arrive at this system whenever this is not ideally suited to be 100% in alignment with some axis as prescribed? So this is what the linear discriminant analysis does. We're going to zoom in on this for a second. The linear discriminant analysis, look at these two clusters up here. Cluster 1 and cluster 2. From this axis, they're pretty overlapped, right? And from this axis, they're a little better, but there's still some overlap, right? So if I come at it from this side, I say, well, there's going to be some blue and some red here, right? So their separability is okay, but not great. Come from this axis, also separability not great. Linear discriminant analysis says, you know what? As long as I rotate everything symmetrically via the same process, as long as I treat all of the data the same, I can apply any transformation I like to it that is just a rescaling or rotational adjustment, right? I could rotate any data set, and that data set is still internally correlate similar, right? From point to point, the relationships from point to point maintain consistency. So anything that I do to the data that maintains the interrelational characteristics of the system is okay. It actually keeps the informational characteristics of the data intact despite the transformation. So we call these retaining transforms, right? So the transform retains information. So this transformation is one that is a rotational transform that's based upon the information characteristics of the system, such that we attempt to do two things simultaneously, all right? From an equational standpoint, I can show you what this looks like for the min-max, but I'm going to just talk about min-max for just a moment. I'm going to say I'm going to attempt to maximize the within-class spread, maximize the between-class spread and minimize the within-class spread. So I'm going to min one thing and max the other thing. So I want to make each group as tight as it can be, right? And I want to have the means of those two groups maximally separated from one another. So I want class 2 and class 1, I want their means as far away from one another as they can be, and I want their spread, their sigmas, their standard deviations, relative to that particular angle of distribution to be maximized. What happens to these spreads as we rotate the system? What happens to them? right? So as I'm sitting here, I have minimized those two factors, or excuse me, minimized the one factor, maximized the other factor, okay? I always want to say minimize both, but it's not. You're not minimizing. You're maximizing one, minimizing the other. Maximum separation, putting them as far apart from each other as they can be, while at the same time narrowing each of their relative margins. What does that do? It makes the region of separation, it makes the boundary, the linear discriminant here, more definite, right? It makes it more visible, easily visible for our projection. So what we actually do is, implied here, is we're actually going to rotate the data, right? So I just took this other graph and just rotated it to show you that if this is my new axis of projection, what I've done is I took the data as it was previously projected and I turned it. I actually applied rotational transformation. Now that rotational transformation is based upon a sort of angle theta type approach. We're going to look real quick here at what that looks like. So we say that Gaussian density estimate is provided by using FK based upon 2 pi sigma. This is the regular pi. This is pi the analytic number, right? The 3.14, right? So that's not the pi of the distributional pi, right? The prior pi. And then we're going to use a complex version of Bayes' formula to express the baseline of that discriminant, right? We're going to say, if I plug in all the values of the system and I replace f, the density function, with this f system, that I can expand it out and go through a series of cancellations such that I can, if I take the log of that system, I can create a new relationship which I call delta k, right? The delta is the linear function operation, and this becomes what is considered our linear discriminant. It's what allows us to be able to discriminate or tell the difference between the two groups. Systematically, the goal here would be to create a classifier for a 2-class system such that if the unary for 2 pi were in fact similar, we can create, as we said beforehand, the ideal central distribution delta, the ideal linear discriminant, is the region in between each of these two groups. But linear discriminant does that by what? First taking the informational characteristics and then reprojecting them onto a new axis such that we maximize with between class spread and minimize the within class spread. We squeeze each of these down to as narrow as they can become and separate them out as far away from one another. And that process is a optimization, right? It's a multivariate optimization based upon now a density function estimate that becomes generative based upon the data. Once we calculate that density function estimate, once we get that function out, we never have to touch the data again. This discriminant becomes the only value we have to have in order to be able to calculate any changes to that system. So we can calculate all the outputs from those points. All right, we'll come back and we'll finish up talking about this and talking about how we do the perimeter estimation by iteration on Friday. Thank you.
Thank you.
Thank you.